In this video, we will present an introduction to functions. Now, as we begin this topic, we first must discuss relations. Now, what is a relation? Well, in everyday life, a relation would be a connection between two people. It's a pairing of people or things. And in the math context, it's the same kind of idea, where it's a connection or a pairing of an x and a y value. So our definition here in math is a set of ordered pairs. Some examples of this would be, a set of ordered pairs, or it could be a table that can be converted into a set of ordered pairs. Like here we see days of the week and temperature. We could take each line of data and create an ordered pair with that. So Monday, for example, is 87, and then Tuesday is 87 as well, then Wednesday is 86, and etc. We can create ordered pairs from the data. Another example would be an equation like this. This would be a relation because, even though it's an equation, we can plug in numbers for x. Let's say we plugged a 0 in for x. We can get back out a number for y, which in this case would be 3. Or you can plug a 1 in for x, and you get 8 out for y. You can plug in any number for x and get out some number for y, thus creating a set of ordered pairs. All right, so a relation would be, by definition, a set of ordered pairs. Now we have a special kind of relation called a function. And our definition of function is a relation in which no two ordered pairs have the same first coordinate and different second coordinates. Now let's try to rephrase that, something a little more simple. We can rephrase this to say, every x value is paired with only one y value. So that's your definition of function. And we'll see some examples of this in a moment. Now, with functions, we have what is called the domain, which would be that the set of first coordinates, or also called independent variables. And these would be your x values. So if you have a list of ordered pairs, all the x values together would be your domain. And those x values are also called independent variables. And then you have what is called the range. The range is the set of second coordinates, also called your dependent variables, which are your y values. All right, so if you have a set of ordered pairs, let's say we had 1, 3, and then let's say we had 2, 6. If that was your set of ordered pairs, your domain would be the numbers 1 and 2. Those are the x values. And the range would be the numbers 3 and 6, because those are the y values. That's a 3 and a 6. All right, so domain would be your x values, range is the y values. And if you want maybe a dumb way to remember the difference between domain and range, sometimes you might remember the terms but forget which one is which one is x, which one is y. The way I personally remember the difference between the two is domain comes before the word range in the alphabet or in the dictionary, right? D comes before R, right? While x also comes before y in the dictionary. So the ones that come first, domain and x, those go together, and then the ones that come second, so the range and y, those terms go together. So that's one way to remember. As long as you have your own method, that's fine. That may be helpful for some of you. So now, how do you identify a function? Well, here we're going to show a few examples where we need to determine if the following relations are a function. And here in this example, we have 3 ordered pairs. Now remember, to be a function, our set of ordered pairs must have each x value paired with only one y value. So if you look here at the number 2, 2 is paired with a 3, but 2 is also paired with a -1. The x value of 2 is paired with both a 3 and -1, which makes this not a function, because each x value is not paired with only one y value. If instead, if this number 2 were, say, a 4, for example, that would be a function, because now each x value is paired with only one y value. Our second example is an equation. Here we have 2x plus y equals -12. And first off, this would be a relation because we could create a set of ordered pairs from this equation. All right, this equation would be graphed to create a line, which a line is just a set of infinite number of ordered pairs plotted. So this would be a relation, and it would also be a function, because whatever I plug in for x, let's say you plug in the number 0 for x, we're only going to get one answer back out for y. Okay, there's only one answer for each x value. So because of that, that would be a function. Now what about this one, where we have y squared equals x plus 4? Well, if you think through this one, let's say we plug in a 5 for x. If you plug in a 5 for x, what we have is y squared equals 9. And then y could equal the square root of 9, which would be a positive or a negative 3. So for that one x value of 5, we actually have two different y values. We have positive 3 or negative 3. So because of that, this would not be a function, because our x value is not paired with only one y value. In this case, we have two y values. Let's try another example. Here we have a mapping diagram, and the question is this a function or not? And this one would be, because each x value is paired with only one y value. This left side over here, this would be your domain. This is your x values. And then the right side over here, that is your range or y values. So look at -1, it's paired only with a -2. 0 is only paired with the -4, and 1 is paired only with the -3. Each of those x values is paired with only one y value. So yes, this would be a function. What would not be a function is if you had an arrow going, say, from 0 to -4 and from 0 to -3. That would not be a function, because we have this x value of 0 paired with two numbers, or more than one. So that would not be a function in that case. Now on the topic of functions, we have what is called function notation. And this is a way to express a function. So the way we write a function is in this manner, where we have a letter, so like f, could be g, could be h, and then in parentheses we have the letter x. Okay, so this can be stated in English as f of x. It doesn't mean f times x. That's a common mistake people make. It doesn't mean multiplication. This is just a way to express a function. And another way of expressing this in English is the value of f at x. So this notation can be kind of strange to get used to, but we'll get some practice with it here in a little bit. But what we can state here is that we have an element in the range of f that corresponds to the domain element x. So notice that. So domain element x. So whatever's in the parentheses is your domain, or domain element. That's your x value, so to speak. And then the letter f is like your range value or y value. So what does that mean, or what does that look like in an actual scenario? Well, here we have f of x equals 3x plus 1. Okay, so this can also be stated as y equals 3x plus 1. So it's another way of stating an equation. So instead of f of x, you could replace it with y. So if I said find f of 1, what this means in English is find the value of y when x equals 1. You can think of it in that manner, where the number inside here is replaced for x. So that's your x value. And then what we're trying to do is trying to figure out your y value when you plug that in. So all you do to determine what is f of 1 is you plug a 1 in place of x. So instead of 3 times x plus 1, we have 3 times 1 plus 1. And 3 times 1 is 3, 3 plus 1 is 4. So f of 1, we would say, equals 4. Let's try another example. Here we have f of 3 times a. So again, if we are told that f of x equals 3x plus 1, right here, 3a, that is your x value. You plug that in place of x. So instead of 3 times x plus 1, we have 3 times 3a plus 1. And that would give you 9a plus 1. So f of 3a equals 9a plus 1. Now try this one. What if we had f of a plus 3? What would that equal? Well, what we do is we plug in a plus 3 in place of x in the f function. So again, instead of 3 times x plus 1, we have 3 times a plus 3 plus 1. And then we can distribute the 3. We have 3a plus 9. So 3a plus 9, and then plus the 1. And then 9 plus 1 is 10. So your answer would be 3a plus 10. Here's another example. What if we had f of a plus f of 3? So if you break this apart piece by piece, f of a would mean that we plug in a in place of x over here. So instead of 3 times x plus 1, we have 3 times a plus 1. And then plus f of 3. So what is f of 3? Well, we plug a 3 in place of x. We have 3 times 3 plus 1. So that would give you 10. So we have 3a plus 1 plus 9 plus 1, which is plus 10. And then 1 plus 10 is 11. So we have 3a plus 11 as our answer. So f of a plus f of 3 is 3a plus 11. Now back on the topic of domain. Let's discuss in more detail the domain of a function. So another way of expressing the domain is the set of all real numbers for which the function makes sense and yields real numbers. So another way of maybe expressing that definition is what numbers can we plug in for x? Okay, domain are your x values. So what can we plug in for x? So each equation is going to be a little different, and typically you can plug in most numbers for x, but there may be limitations. So here we have an example of f of x equals x minus 2 over x squared plus 2x plus 1. So here we can plug in most any number for x, but we are limited by the denominator because your denominator can never equal 0, right? If it's equal to 0, it's going to be undefined. Anything over 0 is undefined. So x squared plus 2x plus 1 cannot equal 0. So what we can do is we can figure out what numbers would make the denominator equal to 0, and those would be values that are excluded from the domain. So if we take x squared plus 2x plus 1 and set it equal to 0, we can solve this for x to see what numbers are excluded. So here we're assuming you know how to factor or solve a quadratic equation, and here in this example we can factor to get x plus 1 times x plus 1 equals 0. And then you set each part equal to 0. So either x plus 1 equals 0 or x plus 1 equals 0, which is the same thing, and that would solve to get x equals negative 1. So x equals negative 1, that is numbers that are excluded. We cannot have x equaling negative 1. All right, so we can say the domain is all real numbers except x equals negative 1. Because when you have negative 1 for x, that makes the denominator equal to 0. And a quicker way of expressing that mathematically is we can just simply write x is not equal to negative 1. So that literally means that x can be any number except negative 1. So that's what you do with fractions. We just have to figure out what numbers are excluded, because we can plug in any number for x except for things that make the denominator equal to 0. Here's another example with a radical. Here we have f of x equals the square root of x minus 2. So again, we have pretty much anything can be plugged in for x, but we are limited. And in this case, our limitations is the fact that our number inside the radical cannot be negative. If it's negative, then it's going to be an imaginary number, because the square root of a negative number is imaginary. And we're trying to find what real numbers can we plug in for the domain. So what we need is x minus 2. We need that to be positive, which means, or I guess not negative. So it needs to be greater than or equal to 0. So that's our limit, our limitation on this. So if we solve this little inequality for x, just add 2 to both sides, what we have is x is greater than or equal to 2. So that is your domain. the domain must be greater than or equal to 2. We can express it like this, or we can express it in interval notation, where it's anything from 2 all the way to infinity. We see that expressed right here. So it could include 2, so we use the bracket, meaning it can include the number 2. That's where we start, and then comma, and it goes all the way to positive infinity. And we never can actually reach infinity. It keeps going on forever and ever. So we put a parentheses around the infinity, showing that it never actually reaches it, but it gets really close. All right, so that would be the same thing, but in interval notation. So make sure you can figure out the domain of a function, and you do that again by finding what values are excluded. Next, we're going to talk about the graph of a function. So here we're told to graph the equation y equals the square root of x minus 3. Now for any graph, okay, you can figure out how to graph by plugging in different numbers for either x or for y. And then whatever you plug in, you can then solve for the other variable. So here we want to plug in things for x. That's the simplest. So let's say we plug in a 0 for x. We plug a 0 in, and then we have the square root of 0 minus 3, which would be negative 3. So when x is 0, y is negative 3. If we plug a 1 in for x, we have the square root of 1 minus 3, which would be 1 minus 3, or negative 2. Then if you plug in a 4 for x, the square root of 4 minus 3 would equal 2 minus 3, or negative 1. So when x is 4, y is negative 1. We can keep going. If we plug a 9 in, we have the square root of 9 minus 3, which would be 0. And then if you plug in, say, a negative 1 in for x, plug in some negative number, that's going to be undefined, right? So if you plug in negative 1, the square root of negative 1 is undefined, so that would not be a point. So it's going to start here at 0, negative 3, and then you plug in the other points. We get 1, negative 2, 4, negative 1, 9, 0, and then connect the dots, and this would make a curve like this. All right, so this would be your graph of this function. Now we're going to increase the difficulty and learn how to graph what is called a piecewise function. And what this is a function that has different parts to it, or different pieces to it. So it's going to look like this. All right, we have basically 3 different functions. We have here, this first line says f of x equals x plus 2 when x is less than negative 2. And then here, f of x equals x squared within the range of negative 2 to 1 for x. And this third line says that when x is greater than 1, f of x is going to equal negative 3x plus 4. So what we do is we can graph each of these functions, but only graph the part that we need. So what does that look like? Well, here if we do f of x equals x plus 2, this first line. Okay, that would be the same thing as y equals x plus 2. So how would you graph that? Well, that would go up 2 on the y-axis. Your y-intercept is 2. Your slope is 1 over 1. So you go up 1 over to the right 1. And you would create a line connecting those dots. However, this line is only going to hold when x is less than negative 2. So x is less than negative 2. That's going to be right here, right? So what we do is we create the line that we would have. So instead of connecting, all the way, going like this all the way through, we just want this part down here where x is less than negative 2. So notice, by the way, it's not going to actually equal negative 2, right? It's just less than negative 2. So right at negative 2, where this graph is at that point, we have to put an open circle there because it's not actually equal to negative 2. It's going to be really close to it, though. So we put open circle to indicate that it's not equal to negative 2. All right, and then we look at the next line. So here it says that y equals x squared. Okay, so y equals x squared would normally be here, and you'd have points like this, and it would look something like this. Okay, that would be your typical graph, but what we want is that graph only within the range, or domain, I guess, values for x, between -2 and 1. So right here at -2, so -2, when x is -2, that's this point right here. We just want the part from here all the way to +1, which would be right here at that location. So what we want is just this part of the graph right here. All right, so that's all we want. So this would be that second part. And by the way, notice we have a closed circle at -2 and +1 because it has an equal sign here for both of those. So that does include those points of -2 and +1. And then finally, this last line right here, we have y equals -3x plus 4. If you were to graph the entire line, you have to go up 4, 1, 2, 3, 4, right here. And then your slope is -3/1. So you go down 3, 1, 2, 3, to the right 1, that takes you here, right at this point. And we'll do that in red so you can tell the difference. So it goes from here to here, and it normally would be, a line all the way through like this. But what we want is the line only when x is bigger than 1. So looking on the x-axis, right here, where x is greater than 1, okay, it's going to be just this part from here down. So we can erase everything else and just have this line right here. All right, so this would be your piecewise function. You graph each piece separately within the domain given to you for x. All right, so everyone's going to be a little bit different, but this is what this graph would look like. Okay, now going back again to the domain topic, here we are told to find a domain value given a range value. So what we're trying to do is figure out what is x given a certain value for y. So here we are told to find the value a in the domain f of x equals x squared plus 2x minus 1, for which f of a equals 7. All right, so this one is a little backwards because we're trying to find the domain value, so we're trying to find x when you're given a y value. So the other examples that we did previously in the lesson was going the other way. You were given a domain value and you're trying to find a range value. So what you do here is, if you're trying to find for which value a do we have f of a equals 7, what we do is realize with this notation, f of a equals 7, a is your x value. So anywhere I see an x, I put an a. So instead of x squared, we would have a squared. Instead of 2 times x, we have 2 times a. And then minus 1 would just be minus 1. And then the 7, this is like your y value. Okay, that's what f of a equals. Remember that notation means y equals. So basically what we're doing is replacing the f of x here with a 7. So that's basically what we're doing. We're plugging that in. And then we have to solve this for a. And we see that typed up right here. So what we do with a quadratic equation like this, we can set it equal to 0 by bringing the 7 to the left, and we do that by subtracting. So now we have a squared plus 2a minus 8 equals 0. And then we can solve by factoring the left side. When we factor, we would have a plus 4 times a minus 2 equals 0. And then we set each part equal to 0. So a plus 4 could equal 0, or a minus 2 could equal 0. And then you solve, so a would equal -4, or a would equal +2. So we've answered the question. We found the value a in this domain for which f of a equals 7. So your answer would be -4 or +2. Next, we're going to talk about the zero of a function. So the zero of a function is basically the solution, I guess, or it's going to be, in other words, the x-intercepts, where it's going to cross the x-axis. So in math notation, we can say a value a in the domain of a function f for which f of a equals 0 is called a zero of f. So the idea here is f of a equals 0. That notation means y equals 0. So y would equal 0 anywhere on the x-axis. right? So if you had an equation like this or a graph like this, where is y equal to 0? Well, it's going to be here and here on that x-axis. So we're trying to find the x-intercepts. Is also many times called the roots. So all that is the same thing. The 0 of a function is the same thing as the root, same thing as the x-intercepts. It's all the same expression. So as we stated, for the 0 of a function, y will equal 0. So if you were told to find the zeros of a function, what we do is we plug a 0 in place of y. And remember, with function notation, f of x is the same thing as y. So in place of f of x, we put a 0. So now we have 0 equals x squared plus 3x minus 18, and then we can solve. So we can solve this one by factoring. We would have x plus 6 times x minus 3 equals 0. Then you set each part equal to 0. So either x plus 6 would be 0 or x minus 3 equals 0. So x would equal negative 6 or positive 3. So the zeros of that function would be negative 6 and positive 3. That is where it crosses the x-axis. Now another thing when you're dealing with the graph of a function is we can test to see if something is a function or not by looking at the graph. And what we do is we perform what is called the vertical line test. So our definition of this test says that a graph is the graph of a function if and only if no vertical line intersects the graph at more than one point. So what does that look like? Well, here's an example where we have this white curve is our relation. We're trying to determine, is this a function or not? So what you can do is you can imagine drawing vertical lines through this graph. And if you draw a vertical line anywhere on the graph, it can only hit one point at a time to be a function. Well, here notice it's hitting 2 spots, right? So because it's hitting more than one location, this is not a function. If you look at the second example, this one would be a function because if I draw a vertical line, say I draw one right here, for example, it's only hitting at one point. If I draw a line here, it's only hitting at one point on the graph. Doesn't matter where I draw my vertical line, it's only hitting at one point. Therefore, this is a function. So if you have the graph of a relation, we can determine very quickly if it is a function or not. Now, when you're graphing, we have what is called increasing, decreasing, and constant functions. So increasing is the idea of something going kind of like this, where it's going to be going up in this direction. It doesn't have to be a straight line, but it could be, it's got to be continuously going in that direction. Okay, decreasing would be something like this. It's going further down as you go to the right. And again, it doesn't have to be a straight line. It could be a curve as long as it's going down. All right, and then a constant function would be something that goes at a constant rate. And this is the idea of graphing something like, say, x equals, let's try y equals 2. If you graph that, okay, you're graphing a constant. It's a number, right? So it's going to be a horizontal line like this. So something like that would be a constant function. Now, the math notation for these definitions can be kind of confusing to interpret, but here it is for the increasing function. Here it says f is increasing on the interval L if f of a is less than f of b when a is less than b. So what does that mean? Well, it means kind of what we said, but so here a is less than b. This would be like your two x values. So say we had 2 points. So let's say we have 2 points, a, and then f of a. That's 1 point. And then we have b, and then f of b. That's your second point. So if your x value, if a, your first point, is less than b, so say we have a point here, let's say that would be your first point, point 1. and then we have point 2 right here. Something like this, where you pick 2 points on this function, and notice on point 1, a is less than b, right? Your x value for a for this point 1 is smaller than the x value for point 2. So that part is true. But we also need, with that scenario, we want f of a to be less than f of b. So we want the y value for each point, for point a, point 1, to be less than the y value for point 2. And we find that to be true as well. So point 1, the y value is down here, whereas point 2, the y value is up here. So the y value is less than the y value for point 2 when your x value for point 1 is less than the x value for point 2. So it's kind of confusing to interpret that, but that's kind of the gist of it. So if you connect those points, we notice that the graph is increasing or going up in that direction. And then for a decreasing function, it's going to be the opposite. All right, so here in math notation, a function is decreasing on the interval I if f of a is greater than f of b when a is less than b. So again, we're using those same 2 points, those same ideas. So we have like a and then f of a, and then we have b and f of b. Those are like your 2 points. For this one, if we had a point here and a point here, okay, and this would be like a f of a, this would be b f of b. So a is less than b, right? A is less than b, is your x value is less than the x value for point 2. Okay, so that would be true, but notice your y values. F of a, the y value, is bigger for point 1, so bigger, greater than the y value for point 2, than f of b. So notice that is true, and the graph we have is something like this, that is decreasing or going down. And then for the constant function, so here we have f of a equals f of b for all a and b. So the y values must be the same. So again, meaning if you have your graph, y must stay the same for all a and b. Doesn't matter what 2 points you pick, your y values must be the same, thus creating a horizontal line like that. So that would be a constant function. Next we have what is called a one-to-one function. So the easiest way to explain this would be remembering that a function, by definition, is a relation that has each x value paired with only one y value. To be one-to-one function, that same thing must be true. Each x value must be paired with only one y value, but the converse must also be true, where each y value is also paired with only one x value. So that is probably the simplest way to explain it. So that is the simple way to understand the definition. And of course, with math, we always make things more difficult, but here is the math definition. We can say a function f is one-to-one if and only if f of a equals f of b implies that a equals b. And we're actually going to use this definition here in a moment to determine if a function is one-to-one or not. And as we already stated, we said that it must be a function, and with the function, each y value must also be paired with only one x value. So we're going to work through an example or two with determining if something is one-to-one or not. Here is a function, f of x equals 3x minus 4. To determine if this function is one-to-one, we want to use our definition. So we're going to use this part here that says f of a equals f of b. We're going to do that part with this function and see what we get for a and b. So if you do this part, so f of a and f of b. F of a means you have 3 times a minus 4. F of b means you would have 3 times b minus 4. So if you set those equal, if f of a equals f of b, so 3a minus 4 equals 3b minus 4, what is the relationship between a and b? Will it be the fact that a equals b, or would be something different. So let's try to add 4 to both sides. That would give you 3a equals 3b. Divide both sides by 3, and notice we do indeed have a equaling b. So yes, we have verified that this is 1-to-1 because f of a equals f of b means that a equals b. We verified that. And here we see all the steps in our answer typed up here in the notes. We're going to try another example. We have now f of x equals x squared minus 2. So again, we want to determine, is this function 1-to-1? So what we do is we want to determine or plug in f of a and set it equal to f of b. So what is f of a? Well, with this function, that means you plug a in for x. So we have a squared minus 2. F of b means you plug a b in for x. So we'd have b squared minus 2. So if you set f of a equals to f of b, then that would mean that we have a squared minus 2 equals b squared minus 2. So now we can try to see what happens, see what the relationship is with a and b. We can do that by adding 2 to both sides. We now have a squared equals b squared. And then if you solve for a, you take the square root of both sides. So a would equal the square root of b squared. Well, the square root of b squared could be a positive b or it could be a negative b. So you have 2 different possibilities here. So it's not, it does not imply that a equals b, because a could equal negative b as well. So because of that, this would not be 1-to-1. So this is if you're given an equation and you were to determine if something is 1-to-1. Now what if you had the graph of the equation? Well, what we can do is we can perform the horizontal line test. So the vertical line test was used to determine if something is a function. So if it passes the vertical line test, meaning it's a function, we can then take it one step further to determine if the function is 1-to-1 by performing a horizontal line test. So it's the same thing as a vertical line test, except now we're creating a horizontal line. And here the definition of the test is that if every horizontal line intersects the graph of a function at most once, then the function is 1-to-1. So here's a graph. We see this line right here, this white line. So this needs to pass the vertical line test to be a function, but then also needs to pass the horizontal line test. So the vertical line test, it would pass because if we create vertical lines, it's only hitting one point at a time, right? So it does pass a vertical line test, meaning this is a function. Now to be a 1-to-1 function, we need to create horizontal lines and see if the same thing happens with horizontal lines. Is it hitting only one point at a time? Well, yes, it would. Any line I create, any horizontal line, is only hitting one point at a time. So this function would be 1-to-1. Now what about this graph? So first off, it would be a function because it passes the vertical line test. You can create a vertical line anywhere and it's only hitting at one point at a time. So it is a function, and then we can take it a step further and determine if it is a 1-to-1 function by creating horizontal lines and see does it hit only one point at a time with horizontal lines. Well, in this case it does not, right? It's going to hit here and here with that line I just drew. If I draw this line here, it's hitting at 2 points again. So because it's hitting at more than 1 point at a time with a horizontal line, this function is not 1-to-1. Now we're going to talk about a different kind of function, and this is called the greatest integer function. So by definition, what this is it's the greatest integer that is less than or equal to x. And the notation for that is right here, where you have something inside of brackets. Or you could express it with this fancy bracket right here around the x, or you can write it as int and then parentheses x. This is like integer of x. So any of these three notations are acceptable for the greatest integer function. Now how does this work? Well, for example, if we had the number 2, we put that inside the bracket. Okay, the greatest integer that is less than or equal to x, so that is greater than or equal to 2, or sorry, less than or equal to 2, would be 2. Okay, because it's equal to 2. Well, what about 2.25? Well, the integer that is less than or equal to x, the greatest number that we have would be 2, right? Because it's got to be an integer. It's got to be a whole number. It cannot be a decimal or a fraction. If we had 2.5, same thing. Okay, the biggest number that is less than or equal to 2.5 would be 2. Now, what if we had the greatest integer that is less than or equal to 4.9? All right, well, this one would be 4 because that is the biggest integer that is less than 4.9. So it's not rounding, it's what number is the biggest number that is less than or equal to the number in the brackets. Now what about with negative numbers? Well, here we have -5 inside of the brackets. So what is the greatest integer that is less than or equal to -5? That's going to be -5. Okay, it's equal to it, so that's fine. Now if we had a decimal, a negative decimal, let's say we had -5.25 in the brackets. So be careful with the negatives, because if you think through on a number line, we have 1, 2, 3, 4, 5, 6. So -5.25 is right here. All right, the biggest number that is less than or equal to -5.25, it's got to be less than that this way. That's going to be -6. Right, it's not -5. -5 is bigger than x, bigger than -5.25, but we want the biggest number that is less than -5.25, which would be -6. Same thing if we had -3/2. Okay, -3/2 is -1.5, which would be right here between -1 and -2. And the greatest integer that is less than or equal to that would be -2. Right, it's the greatest integer that is less than -1.5. Now in general, we can write this function as f of x equals, and then we put x inside of the brackets. So f of x equals this. Now how do you graph something like this? Let's say here's our coordinate plane. And let's start putting in some numbers here. So 1, 2, 3, 4, 5, negative, and then up here. All right, so if you start plugging in numbers, so here we had some, so like 2 equals 2. So if you put a 2 in for x, you get a 2 out for y. So that would work. We could plot that really quick. 2.25, you plug that in for x, and you get out a 2 as well. So if you plot 2.5 comma 2, that's going to be up here, horizontal with that other point. Same thing with 2.5. Basically anything all the way till 3 is going to be horizontal. And then right at 3, okay, it's not going to ever equal 3, but once you reach 3, it's going to pop up. So if you plug a 3 in for x, so the greatest integer less than or equal to 3, it's going to pop up now to 3. You can get really close to 2 to 3. You can have like 2.99, and that's still going to be 2 because that is the greatest number that is less than or equal to 2.99. So it's going to get really close to 3, but it's never actually going to equal 3 for y until you hit 3 for x. Once you plug a 3 in for x, you're going to pop up here to the next line, and you get that point of 3 comma 3. And then you can plug in things for x that are bigger than 3, like 3.1, 3.5. If you plug anything like that in, it was going to equal 3 until we hit 4, until we do 4 inside the brackets. So then that's going to be another horizontal line until you reach 4. And once you hit 4, it's going to pop up to 4 for the y value as well. So what it's going to do is it's going to create these stair-step effect, and it's going to look like this. Let me see this picture a little more clearly. It's going to have this effect. It's going to be stair-stepped up. All right, so this is how you'd graph a greatest integer function. Now this seems kind of weird and maybe a little random, but this actually has application. So here's an example of an application of the greatest integer function. And here we have a salesman who receives a $50 bonus for each $1,000 in sales made in 1 week. If he makes $12,480 of sales in 1 week, how much would he make in bonuses? So what we can do is we can express this as a greatest integer function. All right, so he gets paid for every $1,000 in sales. So he gets $50 times whatever, however many $1,000 sales he makes. So if you take whatever he sells, divide by 1,000, that's going to be the number of $1,000 sales he makes. But it's got to be in $1,000 increments. So for example, if he sells, let's say, $1,200 worth of stuff, okay, he's only going to get the bonus for $1,000 because he has not reached that threshold of the next bonus, right? Each $1,000 he gets a bonus. So he gets it at 1,000, 2,000, 3,000. Anything in between, he does not get a bonus for. So this is the idea of the greatest integer function, because if he got, say, $1,200 in sales, okay, we need to find the number that is less than or equal to that number in increments of 1,000. All right, so the idea here is we take 50 times and then the greatest integer of x over 1,000. And we see that typed up right here. So here he sold $12,480. That can be plugged in for x. So if you divide 12,480 by 1,000, we have 12.48. So that's the number of $1,000 increments that he has sold. But he only gets paid for each threshold that he makes. So he's not reached the 13 threshold yet. He's not made $13,000. He's only made 12,000 plus the 480. So you have to round this down to the nearest whole number, the nearest integer. So that's why it's a greatest integer function. So the 12.48 will become 12, and then we do 50 times 12, which is 600. So that means that the salesman would receive a $600 bonus. Here is another application, but this is more of a general application from the lesson, not specific to the greatest integer function. And here we are told that an open box is to be made from a 36-inch square piece of cardboard. To make the box, you must make a square from each corner that measures x inches. Write the volume of the box as a function of x and determine the domain of x. All right, so this one will be definitely helpful if you draw a picture. So here we have a box, okay? And I guess we should put the word fold in here. You must fold a square from each corner that measures x inches. So you're kind of folding this up to make the box, right? This is a flat piece of cardboard. You can fold it, and you're going to fold it in this manner along those dotted lines. So we can start labeling this picture, and it says that the box is made from a 36-inch square piece of cardboard. So that's meaning that each side is 36 inches. All right, so this is 36 inches, and then we are also told that we are making the box by folding a square from each corner that measures in x inches. So meaning this right here, that's going to be x, this little part is x, and the same thing on the other side of the square as well. All right, so we have our diagram here. Now if you look at this dotted line, this is going to be the dimensions of the box when it's folded, right? So you're going to fold each edge up to make the box. So when you do that, your dimensions would be here, the dotted lines that we see. So what is the length of one of those dotted lines? Well, the entire length of the cardboard is 36 inches, and then we're subtracting out this x and then this other x right here. right? So this would be 36 minus the 2x's. So each of those dotted lines would be 36 minus 2x. And then when you fold it together, it's going to be a box like this, all right, where each side is 36 minus 2x, and then this height here is going to be x. That was the height from folding it up. And now we are trying to write the volume of the box as a function of x and then determine the domain of x. So the volume of a box, or a prism, would be found by doing length times width times height. So the area of the base, area of the bottom, times the height of the prism. So what we have is 36 minus 2x times 36 minus 2x times the height, which is x. So we have 36 minus 2x squared times x. And we can just leave our formula like this. We could simplify if we wanted to, but it's not really necessary. So this would be our formula, or our function. And we could swap out the v for f of x if you wanted to write it more in function notation, but it's kind of the same thing. All right, now from here we can figure out the domain. So the domain is the values for x. So what must x equal, or what could x equal? Well, we know x cannot be negative, right? Because x here is a height. It's the height of the box. So x has to be greater than or equal to 0, and probably we should say greater than 0. So it's greater than 0. And then, is there any other limitations? Well, we also know that 36 minus 2x, that length must be bigger than 0. Okay, because that's a length. It can't be negative length, right? So we can solve this. So we can subtract 36 to the right side. So we have negative 2x is greater than negative 36. And then divide both sides by negative 2. So now we have x on the left, 18 on the right. And then dividing by a negative flips the inequality from a greater than to a less than. So we know that x must be greater than 0 and less than 18. You can write it as a compound inequality where x is between 0 and 18. So this would be your domain. X must be between 0 and 18. Anything bigger than 18 would not work. So it's got to be within that domain. And that concludes our lesson for today. We will see you next time.